In my videos, I'm often being sloppy with variable initialization in C, and I often get comments like, dude, you need to initialize your variables. And I usually respond with, man, this is just an example. I don't want to make my example code too bloated. But I guess it is time to talk about variable initialization. So let's take a look at this code. Just the three variables, a pointer to an integer, a double, and a character string. And we printf it with %p to print a pointer, %f and %s. And if we compile this, main.c, and run it, we get nil, zeros, and null. Intuitively, it makes sense, right? We didn't assign this to anything, so naturally we get zero value. Let's keep pushing. Let's call a function named foo. And a function that is named foo, we are going to define it here, so void foo. It's not gonna take anything. So we are creating the same variables as here and trying to print them. And let's compile the program and let's run it again. And what are we getting here? We are actually getting a segfault by trying to do the same thing. Look, our first invocation in main just printed some zeros, but our second invocation crashed the program. So let's debug it. We need to compile our program with the debug information -g, and now we should be able to just run gdb, and yes, there we have it. So let's put a breakpoint here and let's run our program. So here we are stopping on printf, and we see that in our locals window all variables are initialized to 0. And also, I guess let's pop up a gdb, how does it call, disassembly in a separate frame. Yeah, so there you go. Let's put it somewhere here on the side, set a bigger font here. Yeah, there we go. So here is our disassembly of our code, and here is a tiny breakpoint if you can see it. So here we are staying on a code that pops a bunch of stuff from the stack pointer. And this is how printf works, right? So yeah, you can see that it does some stuff to assign the values it's about to print into register before calling into printf itself. And if we go up, we can see our push the stack pointer and then move rsp-rbp. This is a standard part of System5 calling convention. And by the way, I have a video where I go deeper into this whole assembly stuff for this architecture. I'm gonna leave it in the video description. You can go check it out. But here, I guess the point is that the assembly is pretty simple. Nothing really happens here. There is no special instructions for initializing these variables. You can see we just popping them from the stack into printf, and then we call printf, and then we will be calling foo. And so let's actually go to calling foo, and let's step into it. So here we are stepping into foo, and we are on this line that will print these variables. And what we can see is that the pointer to int a is 0, but everything else is some kind of garbage. Actually, the debugger gdb is trying to print character star as a valid string, and it can't because the thing that this memory address points to is inaccessible. It probably doesn't belong to our program or something. And here's our assembly, and it looks exactly kind of as our main function did. So what we can see is that in this foo function, half of our variables just contain some garbage because we did not initialize them. And if we go back to main up the stack, we can see that they are initialized to 0. But if you look at assembly, it doesn't really change. So here, me clicking back and forth, and the assembly itself looks exactly the same. Well, apart from our main is calling foo and our foo just doesn't do anything. So what we can conclude here is that our memory is 0 initialized by default in main, but not in the subsequent functions. And if you think about it, it makes sense, because when operating system starts the program, it gives us a chunk of virtual memory that it 0 initializes for us. Because if the operating system didn't do it, Imagine the chaos of programs being able to access some leftover memory from other processes. All hell breaks loose. So for security reasons, it makes sense for operating system to do it. So in our main, we have a pristine clear memory, but everything down the line gets slowly and slowly corrupted by calling functions and doing stuff. So that's why in foo, we already start seeing some artifacts. So yeah, I guess end of the video, right? Set your variables to something or they will get garbage. And kinda yes, and if that satisfies your curiosity, thanks for watching, I guess, but maybe let's dig a little bit deeper here. Huge disclaimer before we continue, I am not an expert in assembly. I should have probably said it at the start of the video, but then nobody would have clicked. And second of all, none of what I'm showing here is guaranteed by C standard. This is what they called a undefined behavior. I have a problem with terminology, but more or less the actual assembly that is generated in this particular case and what you see in the output is compiler specific implementation because it is not defined by C standard. GCC and Clang without optimizations produce the same code here, but different platforms, different architectures, different compiler flags will be different. As a matter of fact, if you compile the same program with optimization flags, you will see a different output. So with that out of the way, let's continue. So let's define these variables, let's initialize them. First of all, our pointer, we initialize something like int star beef, so we can see it in the debugger. So B is something like 1, 2, 3, 4, 5, 6, 7, and our string will be hello there, General Kenobi. And yes, this is it. After we call foo and exited it, let's call another function. Let's call bar and let's define it, void bar. And for now, it's just going to be empty. Let's go with the debugger for now. Let's go back to our console. Let's recompile our program. And if we run it, now, as expected, we see our variables initialized. Now, if we fill the bar function again with the same three variables, ABC, but we do not initialize it, we just print it as we did in main, what is gonna happen here? Do we crash like we did in foo without initialization, or what's gonna happen? So let's run it and figure it out. And yeah, you need to save the file first. Now, if we recompile it and run it, look at that. So this is our main, this is our foo, and somehow this is our bar. So our bar, despite not initializing the variables, prints exactly the same thing as it did in foo. So what is going on here? And for people who don't know C as much, this is not just about variable names. So if, for example, we rename this to x, y, z and x, y, z, you will get exactly the same output. Yeah, so these variables are fully scoped. They don't leak it or anything like that. Something entirely different is actually going on. So back to debugging mines. Right, let's expand the window, let's run GDB, and let's actually break in foo this time and run our program. Here we are at the start, and you can see that now our local variables contain some garbage before we initialize them. And actually, let's get our disassembly back. And let's look at it. So we are staying on this line, and in disassembly, we are moving, here's our dead beef, to our EX register. Before that, we need to talk about how the stack situation works. So on x86, all of these functions start with prolog, push RBP, move RSP RBP, and then some sub. If we go to main, here they are. If we go to foo, here there are as well. So what happens is that push RBP pushes the caller's base pointer to the stack of our current function, so foo, so we can remember it later. Now it moves RSP to RBP, so it moves current stack pointer to RBP, so we have some kind of a base that we can consistently use. And then this sub reserves space for local variables, and then the body of the function. And at the very end of the function, we have this leave instruction. So what leave instruction does, it actually takes the stack pointer and rolls it back to saved RBP, the RBP that we saved previously, the one that points to our main. And because of that, everything that was allocated here kind of becomes freed. And this is actually what makes stack memory so safe. So you allocate a bunch of stuff on the stack. Usually you can even allocate static arrays. And in C, you never have to free anything you allocate on stack, because the way compiler generates the code does it for you. And also, since we store the base pointer here, we can just pop it right back as a second part of the leave instruction, and we go back to main. And actually, every time we push RBP, debuggers keep track of this information, and this is where this functionality comes from. This is why you have a backtrace that you can travel back and to. Debuggers just preserve and store this information internally, usually as some kind of a linked list or something. So yeah, after all that, we go to our main function body. And let's look at how variables get initialized. So we step over the X, and here we are. So look at this, how the compiler generated it for us. First, we move the value that we assign to the register, and then from this register, so EX and RAX is the same thing, we move it to the stack. Again, we use the new base pointer with some offset, and we put the dead beef on the stack. After that, we go here, so we step over two of them. So we moved our float to XMM register, and then from XMM we put it to RBP. And you might notice that it used XMM register, which is a SIMD register, but this is how modern x86 architecture requires you to work with doubles. And you can also notice that instead of move, there is move SD. SD stands for scalar double. Yeah, so, and if we go to register tab and scroll down a little bit, here is like this. Here's our XMM, and this is our variable. So it is 128-bit register, and first 64 bits are unused. And here's the value, 40FE to 40B, and then a bunch of threes. Don't forget, we are a little endian machine, so you have to read it left to right. And is this actually our value? Let me P/X Y. So I print the value of Y in hex, and yeah, 40 FE to 40B 33333. Yes, there it is. It is actually our Y. And after that, we step again over our character star. There we are, and we just put it, yeah, there you go. So we just put it here on the stack. And yeah, there we have all our XYZ. They are finally initialized, and here is where printf happens. And also, let me actually open a memory window so we can inspect them in the memory. And you can do it in Emacs by memory frame. Also, let me open it in another frame so we have it here just floating around. There you go. So this is our execution stack memory. And let me get the address of this one. So print address of X. So let me copy that and go to this memory address. So this is our dead beef on the stack. And here is our floating point. Yes, so 40FE to 40B and a bunch of threes. So yeah, there you go. Now this is our address of our character star. So you can see it here. So 6008, 60, so yeah, 55555, 6008. So yeah, here is our stack memory as we see it here. So now let's step over print and go back to main and step into bar. So as you can see, now we are back in main, and we are going to step over into bar. And please note the stack memory around the same address. We still have dead beef, we still have our float, and still have the same character star on the stack memory. So even though we popped the base pointer back to main, none of this memory actually gotten cleared. That's why when I said that the compiler frees everything for us, it doesn't actually do it. And I'm going to get cooked for it in the comments, but this is kind of a form of use after free, right? So next stack frame is gonna reuse the same chunk of memory that the previous call used when we step into it. And because the memory layout aligns exactly, this one just get reused the same addresses. And if we go and look at our locals, ABC have the same values that were in foo, because guess what? If you look at assembly, what do you see here? Or rather, what you don't see here? You don't see any calls to memset. You just see a bunch of values popped from RBP for printf, but you don't see any memory gets altered. Because, well, in debug mode, GCC just generates the most straightforward and the most naive code. And if you don't specify a special compiler flags that can zero initialize memory for you, it's not going to do this. And as I said, in your real code, you don't necessarily get the same exact behavior when variables from one function somehow reuse variables from other function. This is just how GCC in debug mode ends up working in this particular contrived example. In your real code, you forget to initialize a variable. It usually has some garbage that gets interpreted in a real way, and it just manifests itself in either some weird and inconsistent crashes or just some weird behavior that you have to debug real hard. That's why modern compiler have all sorts of flags to help you with that. They can warn you on uninitialized variables, they can zero initialize stuff for you, they can do all sorts of things to help you out. And for example, MSVC, it just mem sets uninitialized variables with some kind of a debug pattern like cd, 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 cd. So when you debug your program, you can clearly see, okay, this looks familiar, I just forgot to initialize it somewhere. All right, we figured it out. You need to initialize your variables, but what to initialize them to? What are the best practices? And there are few approaches. My favorite is to initialize everything to zero, and in my software, in my programs, zero initialized memory just has a special meaning. And you can imagine an example. You have some kind of a user management system, and if you have a user struct that you zero initialize, it just becomes an anonymous user. And then all your functions that need to return a user, instead of returning a null pointer, they would return an address of some globally allocated user on the stack that has either everything zeroed out and your program just knows that if something is zero, it is an anonymous user, or maybe you, at the start of your program, you just run a function that initializes anonymous user, and functions just know that if authentication failed, you return address of the struct. And so everything else in your code that accepts a pointer to the user, it doesn't have to check if user is null. It just can assume that it always gets a valid user that can be an anonymous, and this just flattens your code paths by a lot. And same with primitive values. So if you have an index of some assets in your video game, you just reserve index 0 to missing assets. And then if you have some misconfiguration or actually some missing texture, you load your level editor or you load your game and you see magenta texture that you instantly notice. And even if this happens to ship to your users, seeing some magenta texture on a window is probably better than just straight up crashing your game or corrupting the save file, right? But there is also an alternative position to that. Maybe you run a financial database and some weird zero value you probably don't want to propagate it along your system. In this case, maybe you want to explicitly initialize to your target variable, and in every function that accepts it, you would rigorously assert on the entry and maybe on the exit. So here we have an article by Ryan Fleury that heavily advocates for zero initializing everything. I highly recommend to read it. It's pretty long and I'm gonna link it in the description. And the opposite way to think about it comes from the Tiger Style by Tiger Beetle, which is a financial database, and they have a point on assertions. So assert arguments, returns, and invariants. What you expect and don't expect, the positive and negative space, not only contract but breach. And Tiger Style is their coding style in their database and what they advocate for all projects. I'm gonna link it in the description as well. These styles, they don't necessarily contradict, you can use them together, but you can see where they might disagree. And the third one I would also mention is Dependable C by Eskil Steenberg. He actually has a whole article on why zero initialization can be considered harmful. So I don't want to have a strong opinion. I personally kind of lean to zero initialization that Ryan advocates for, but I'm going to link all three because I respect all three sources and all them have value. So mix and match as you see fit for your project. And this is actually why I like Jai so much. So if we go to the folder, I have a Jai program, which is exactly the same. It has foo and a bar, and foo initializes variables, but bar doesn't, and we call foo and a bar without all other craft in main. Well, first of all, let me compile it. So Jai main.jai. And now if we run GDB here, so we run main here, yeah, there we have it, break. Let's actually break straight up in bar. So we run the program and let me open a disassembly. And so if you see printf from foo, it printed deadbeef, float, and the character star. So instead of character star, I put pointer to u8 and return a data part of the string, because in Jai strings are a structure of a count and a data. So Jai uses counted strings. So this is just to level a playing field. And here is our assembly for bar function. And actually you can see that before the code gets here, we have ABC, and they point to deadbeef, the floating point, and this string that we had in foo. So before the code runs, we still have some leftover memories. But as soon as we step in main, let's look at the assembly. Let me step into it. So we are on A here, and let's step over it. And look at the locals. A is now 0. And why is that? Look at this assembly part here. Jai calls memset for us, and it zeroes out the memory by default. And so if we step over B and C, all of them are now 0 because memset, memset, memset. So Jai codifies this 0 is initialization idea at the language level. That's why I like it so much. I don't need to care about memset in the memory. Every time I create a variable, it's just beautiful. And it also gives you a flexibility. If you don't want to memset something, maybe it's something big, right? You can always do this. So triple dash means do not initialize this memory, just leave whatever garbage is in there. So yeah, and of course, if we just continue the program, the second print prints null, 0, and null. This is everything I wanted to show today. Like, subscribe if you enjoyed the video, dislike if you hated it, feel free to correct anything I said wrong in the comments, and remind your colleagues to initialize their variables.